This program was sponsored by the Jesse and John Dans Fund. Since 1962, these lectures have been a forum for distinguished scholars of national and international reputation who have concerned themselves with the impact of science and philosophy on man's perception of a rational universe.
Good evening. My name is Marcia Landau. I'm the Dean of the Graduate School at the University of Washington. And on behalf of the Graduate School and the University, I'm really pleased to welcome all of you here for this evening's Dans lecture. The visiting professorship, the Jesse and John Dans visiting professorship, comes to us as a result of a very generous gift that was made to the University of Washington back in the 1960s. John Dans was an early Seattle pioneer. He was an entrepreneur and is perhaps best known in this region for the chain of movie theaters that he developed in our state and others on the West Coast. John Dans was a self-educated man who read widely and read liberally. He was fascinated by scientific developments and was particularly interested in the philosophy of humanism. In creating this endowment, his goal was to bring distinguished lecturers and scholars of international reputation to the University of Washington. He particularly wanted to have those men and women who, and this is in the words of the endowment, who have concerned themselves with the impact of science and philosophy on man's perception of a rational universe. Mr. Dan's wife, Jessie, shared this vision and augmented the endowment with additional gifts until her own death. Our speaker tonight is James Head, and he will be introduced by a member of the University of Washington faculty. Dr. Don Brownlee is a professor of astronomy. He's also a member of the newly formed astrobiology program. Dr. Brownlee works on extraterrestrial materials. He is the principal investigator on the NASA Stardust mission. That mission was launched last February. It will go out and collect samples from a comet and return those samples to Earth in 2006. Dr. Brownlee has been in the news a lot recently. He is the co-author, along with Peter Ward, who's a professor of geology, of a recently published book that has become a bestseller. It is entitled Rare Earth: Why Advanced Life is Rare in the Universe. Don Brownlee.
It's a great pleasure to introduce Jim Head tonight. He's the Lewis and Elizabeth Shirk Professor in the Department of Geological Sciences at Brown University. And Jim is a true world leader in the field of planetary science. He's had a quite remarkable career. He's very talented and energetic, and he also landed on Earth at just the right time. He has been involved in most of the United States and Soviet missions that have examined the solid surfaces of planets and moons. Since 1973, he has been at Brown University. In 1973 and 74, he was the director of the Lunar Planetary Institute in Houston. In 1968 to 1972, he worked with NASA on a most extraordinary project. You might remember what happened about that time. In my opinion, this is one of the greatest human adventures, the Apollo program, the exploration of the moon. And Jim was heavily involved with this, with astronaut training, landing site selection, traverse planning. The astronauts didn't just drive across the moon. All those movements were carefully planned, seemingly carefully planned. Mission operations and data analysis. Now, for anyone here that is under the tender age of about 40 and may not remember this event too well, I have about a 1-minute clip to show. It's Apollo 15.
Roger. And follow on home.
There's sure a lot of neat rocks in Dune. Too bad we can't spend some more time.
On your next trip.
Yeah, next trip, you're right. Making me seasick.
What do you expect traveling on the Mare?
They returned to the science station where Scott once more manned the drill to place the second heat flow probe and later to get a deep core sample. The difficulty in drilling was shown by Scott's hands, which would carry bruised fingernails from his efforts for several weeks after the mission.
Okay, Dave, take heart. You've got just 1 minute of drilling left.
Okay, we made a little money, didn't we?
Hand over fist.
It was time to get back into the LEM and end EVA-2. The drill and attached sections were left in the ground for removal during the next day's traverse. On Earth, scientists pored over data from the television, from the astronauts' descriptions, and from the orbiting experiments. The 1,400 photographs the crew would return would themselves constitute a major scientific legacy. Lunar exploration was achieving a new maturity. We are now exploring to test new hypotheses, and the pieces were fitting together. One scientist, when asked why he didn't sit down and rest after an around-the-clock session, replied, "I can't, I'm too excited."
Thank you. So I'd also like to say a few other things besides his scientific career. You could cut that off. In looking at Jim's webpage, I found out some things about him that I didn't know. For one thing, he takes courses. Most professors don't take courses. They either figure that if it's important, they already know it, or if they don't know it, it's not important enough for them to learn it. And anyway, on his webpage, it says, "I enjoy taking courses: psychology, biology, political science, social psychology, drawing, baking, and cooking." And he also has some interesting hobbies. "I collect Soviet and other international space memorabilia and beer bottles. The explosive development of microbreweries has regrettably caused me to seriously question whether I will ever achieve the lifelong goal of tasting one of every type of beer brewed in the inner solar system. But the quest goes on." And I told him he came to the right spot. Anyway, welcome, and we're very excited to hear about the planets.
Thank you very much, Don. Thanks especially to the Dance family for bringing me out here and giving me further education. It's been a wonderful day so far, and I'm looking forward to the rest of the week spent in various departments around campus learning from you all. And also, I thank you for that clip, a little bit of deja vu there. I just wish I'd kept that tie. You know, that's Well, planetary exploration has come a long way in the last 30 years, and if I could have the first slide, please. I'd like to start by reviewing a quote that T.S. Eliot made that was, in fact, quite an unusual one and a very profound statement that he made recently, some years ago, actually. And it says, "We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know that place for the first time." Now, these are really important words because it, in fact, shows what perspective really is all about. But why do we need to explore and leave the very place that we're most familiar with, in fact, to get perspective? This is really an important question, and it gets at the very nature of being human, I think. Why can't we see things around us and fully understand them? Well, of course, one reason is that we need more than one data point, simple as that. People, for example. Take people. Not everyone is the same. You learn this as you get older. There's weird Uncle Ralph, you know, then the in-laws. I mean, all you have to do is look around you and see that people are different. People are different in so many different ways, it's incredible. So you need more than one data point to understand what's going on. And of course, places are different too. We know this from a lot of different perspectives. When we explore the planets, you know, we find out that Dorothy was right. We're not in Kansas anymore. And in fact, things are very different where we go, and things we see or give us perspective. And thirdly, things. As we look at plants, animals, in fact, at planets, we find that each new data point brings us something different and an amazing perspective. A second reason we need this perspective is that processes are commonly not deterministic. Geological processes, all sorts of processes, biological ones, etc. Take evolution, for example. Of course, I was brought up with the idea of the tree of life, with humans comfortably placed as the ultimate crowning achievement of billions of years of evolution. In fact, we're probably not that way. We probably owe our existence to a chance event, an impact at the Cretaceous-Tertiary boundary. which probably paved the way for a period of mammalian supremacy. That's us, okay, more or less. And in fact, the truth is that small organisms, bacteria and others, in fact, rule the planet and will continue to do so long after humans are gone. And, you know, probably eventually they will be. So forget the tree of life with humans is the ultimate crowning experience. And in fact, it's very different in that perspective. And a third thing is that the only thing constant is change. This is a very difficult lesson for us in many ways, but in fact, it's hard to accept because we like constancy in our lives. But in fact, what we see is when we look at the planets, for example, the kinds of perspectives that we have on planetary evolution, we are not now where we were before, and we will not be in the future where we are now. And the only thing really constant is change. The fourth item is that we're seriously underinformed about the natural world. A colleague of mine and I were sitting in my office one day, and one of my students came in several years ago. She was looking for a master's thesis topic, and she said, as she walked in the door, you could just see her look down the side beyond all the beer bottles at the Lunar and Planetary Science Conference abstracts and proceedings, 1 through 30, and just kind of glaze over at the idea of all this information. And she said, how am I ever going to find a topic that no one's ever thought of before? Well, my colleague, Lionel Wilson, without skipping a beat, said, oh, don't worry, everything is not yet known. You know, this was certainly comforting to her, but in fact, it's true. It's really true. We can only formulate questions about the future and about the unknown from what we know, which places us very close to where we are now. And virtually everything is not yet known. We've only hit the tip of the iceberg, so to speak. And that's very humbling, but very true. That's why the quest must go on. The last item, I think, is that we have an extremely limited view and perspective in time and space. One of my favorite recollections of this is in the series Star Trek, when something beams aboard the Enterprise, and of course, Captain Picard is all kind of flustered about this, you know how he gets. And he looks and he says, Lieutenant Commander Data, what is this thing? Data does the, you know, and says, Captain, this being is not a native of our space-time continuum, which is, you know, a pretty profound statement. And the captain, you know how the Star Trek is, the captain gets a little flustered, does that shirt thing, when he, and then tries to figure out what to do. In fact, the sad truth is that we spend 99% of our time in a very tiny corner of our own space-time continuum. And the next slides illustrate this. If we take a look here at this chart on the left, you can see here a plot of space and time. On the left we have family, city, community, nation, country, and world. And here we have today and this week, the next few years, your lifetime, second generation. The density of the open circles denotes the relative number of people. And you can see here that the density is greatest down here, and as you move up to city and community and up to the world, it gets less and less dense, and out here to second generation. Who among you, you know, actually today thought much about the second generation? Not very many people. I mean, let's face it, we're just simply really caught for very good reasons in the short-term time-space continuum here, and in fact, we really think about short-term things, and this is really well illustrated this. I mean, you know, I'm sure people here are thinking, why do they hold this thing at 7 o'clock? I'm either going to miss dinner or have to eat dinner late. When's he going to show some pictures of planets? You know, is he going to be finished in time for me to go home and see Drew Carey? All the kinds of things that are really important from the point of view of, you know, short-term time. And the trouble is, of course, there are a few people that actually get above this. A couple of people in the audience, I'm sure, are somewhere out here thinking about, you know, is Mount Rainier going to blow soon? And if it does, will the landslides and other things make it all the way to Seattle and so on? But the fact of it is, we're really hardwired to sit in the lower portion of this term. And we think in the short term, and we think locally. Imagine one of our distant ancestors, for example, sitting in the middle of the veldt, trying to think about, you know, the stars and the planets and contemplate what's going on there. You know, it's a safe bet that those genes weren't likely to be passed on to the current gene pool. In fact, you know, lions loved contemplative thinkers in those days. And we just simply, you know, didn't end up with a lot of people like that passing them on. So it's clear why we think that way. But it's very important, if we're going to live up to T.S. Eliot and really get some perspective on things, to press on in spite of all those shortcomings, because there's many, many reasons why they're that way, and there's many reasons to cast those bounds. So let's try to throw off some of those bounds get beyond our own home, shown here on the right, and explore the neighborhood. That's just literally our little neighborhood here, that is this solar system. Is T.S. Eliot correct? Has the last 40 years of futzing around the planets and planetary exploration changed our perspective on our own home planet? Next, please. Actually, there have been two parallel revolutions in the recent past. One of them has to do with getting a perspective on the Earth in terms of the astronauts looking back on that image of the Earth and realizing that they couldn't see national boundaries, in fact, couldn't actually see the kinds of things that meant so much in the short term. That was a real important perspective for us. It made us think about environmental concerns and a whole host of other things that really started to free us from this short-term perspective. And I think that's one of the most monumental images of the last century, for sure. Now, we also had a parallel revolution in understanding the Earth as a planet. Looking back on that body, we could actually see that it was a planetary body, not just a geological this and atmospheric that, but an integrated sphere that worked in ways that we could see for the first time in a true human way from halfway to the moon. Now, one of the things that we found out in a parallel revolution was that, in fact, the Earth operated in a plate tectonics mode. Shown on the left here, you can see the Earth's ocean floor after it's had the oceans removed. And we know now that the ocean floors are incredibly young in terms of the geological history of the Earth. Shown on the right here is an age map, and all this area of the ocean basins, a significant portion of it, is actually formed in the last 1% of Earth history. This tells us that the Earth's an incredibly dynamic planet. Okay, it's moving around at very rapid speeds. The processes are dynamic, and we're lucky because as geologists we can go out and study what's going on. The next slides illustrate some of these processes. We found, for example, next please, we take a look at, this is some of the work we've been doing on the eruptions on Kilauea. You can go out and you can watch things happen, you can make measurements, you can make predictions. It's going to erupt again, it's going on right now. And in fact, unfortunately, you have to watch where you leave your car because when you're looking at the volcano here, you know, the lava, we know this goes downhill and then, you know, you don't park your fuel vehicles there. We also know that there is quite a variation in volcanic activity over the planet. Next slides, please. And you can see, in fact, something you know familiar here, Mount St. Helens eruption, May 18th, 1980, and others around the planet, you know, nice place. This is where we like to check in when we want to study volcanoes. You can see, in fact, that these are quite different than what you're seeing in the other one. So you have two major types of volcanic activity, and they actually correlate with tectonic plate boundaries. We can learn something about the integrated planet as a whole from these kind of interactions. But it's a dynamic planet, an incredibly dynamic planet. Next, please. Now, when we look at the planet as a whole and look inside the planet, we can actually find out what's going on. Plate tectonics and the exploration of the interior of the planet has provided us with amazing insight into what's going on. And we know that, in fact, the crust is forming at mid-ocean ridges, crustal seafloor spreading is going on, continental drift is occurring, plates are coming together, subducting, and being recycled down into the interior of the planet. I mean, these things are moving apart at rates that are more rapid than your fingernails are growing. Of course, this isn't going to make airfares to London go up anytime soon, but mapped out over geological time, this is really incredible. It's moving very rapidly. So one of the big messages about studying the Earth over the last decades is, in fact, that it's an extremely dynamic planet. That's the good news. We can go out and study it and understand it. On the other hand, the bad news is that it's erased the formative years. We do not know what's going on in the early history of the Earth very much from what we see on the surface record. Shown on the right is an example of that. If you think about the Earth as a clock starting here and working around to 12 here, in fact, most of the geological record is in the late evening hours here, sort of between, well, I would even say sort of 10 o'clock on. This represents the percentage of the Earth's surface formed at different times over the history of the Earth. The vast majority of those ocean basins formed in the last few percent of Earth history. You can argue about this down in here and what we've learned, but the first half of solar system history, the first half of Earth history, is virtually unknown in terms of significant volume of rocks that we can look at over the course of the history of the Earth. So this is bad news if you want to know where you came from and where you're going. Next slides, please. On the other hand, the good news is there are other examples out there, and this is, again, why we have to leave the Earth and understand what we are here. This is part of the T.S. Eliot perspective. We can look, in fact, at a variety of other planetary bodies here. Here are the Earth-like planets, the outer planets, and we can look at variations in size and density, presence and absence of an atmosphere, and atmospheric pressure, and position in the solar system, Mercury, Venus, Earth-Moon system, and Mars, and try to learn something about the variables that are creating these planets, the paths they've evolved on, etc. And this is what the last 40 years of exploration of the planets has really done for us. So let's press on and see what we can learn about these things. Is the early history of the planets, in fact, preserved out there? Is what went on Earth out there somewhere a message for us to learn? Next, please. Now, the moon, of course, is the smallest of the terrestrial planetary bodies, and I will go up in size as we move along here. It's 1/4 the diameter of the Earth, small, as you know, from looking up in the sky. On the other hand, we see a tremendous amount that we've learned from this, because in fact the blue dots represent the 6 Apollo landing sites where Apollo astronauts landed and returned samples and explored the surface, and the red dots represent the 3 Soviet lunar sample return mission sites. Well, what did we learn from this? Next, please. The Apollo astronauts, in fact, as Don so nicely pointed out here, did some first-class exploration of the moon. The samples that were returned, the geological context in which they were gathered, and the information wrought from those samples when the astronauts returned them and they were examined by scientists in the labs here at the university and elsewhere around the planet, brought us a whole chronology of what was going on and an understanding of much of the geological processes on the surface of the moon. Shown here is Dave Scott, in fact, at the edge of Hadley Rill, and one of the Apollo 17 astronauts, Jack Schmitt, a geologist astronaut, by the way, at Hadley, at Torres Littoral Valley. Next, please. Now, what did we learn from this? We learned, in fact, that the moon was not characterized by plate tectonics. It was not characterized by activity. The surface was very old. And in fact, rather than plate tectonics of a lateral sense, it had vertical tectonics. Instead of a broken up lithospheric set of plates, it had a single global lithospheric plate that stabilized very early in its history and lasted as such for billions of years. This was good news because it meant that what was going on in that first third of solar system history is preserved, and we can tell from this what probably was going on the surface of the Earth. We saw, in fact, quite a variety of geological units, multispectral images. John Adams here at the university was instrumental in teaching us actually how to understand the clues that came from the spectral data represented here. And it showed a host of volcanic eruptions over billions of years. Next, please. In fact, a second thing it showed was impact cratering and how important impact cratering was. You know, when I was a student, there was a little addendum to the structural textbook that talked about Meteor Crater, Arizona, but it was like way off the radar screen in terms of a significant process. But of course, the astronauts sampled many, many craters. This is only a couple kilometers across. Craters range from microcraters all the way up to large craters such as Oriental here. This is 900 kilometers in diameter. You can see the edge of the moon here. You can imagine how this rearranged the real estate. One of my colleagues, Jerry Wasserberg, said this would have been a heck of a thing to watch from Earth if you had a good bunker, because a significant, small percentage, but a significant amount of ejecta left the planet, okay? This is a big event. These things are very common in the early history of the planet, and they must have occurred on all the other planets as well because we see them there. As a side note, you can imagine what the evolution of human culture would have been like if this thing had been at the sub-Earth point. That is, if you looked up in the sky at the moon and you saw this big eye up there looking back at you, I think the evolution of human culture and religion would have been significantly different than it actually turned out to be. You can imagine, you know, when's it going to blink? You know? What are we going to do when it does blink? I mean, there's all kinds of things you can let your fantasies run. But nonetheless, this taught us that impact cratering was important and scale was quite large, okay? This led us to think about, after a few years, the geology of the moon and the geology of the Earth. And the next slides illustrate the fact that, in fact, there was some convergence on this, the Earth-Moon system. In fact, the prevailing theory is now that the moon actually was part of ejecta from the Earth caused by a Mars-sized object that's twice the size of the moon hitting the Earth very early on, and through a series of events, continuous events here, ejecting material into Earth orbit to form the moon. Now, you know, this is really remarkable. This is a new insight into how the Earth evolved in its early history and how the moon formed. You can imagine, just looking at this last stage here, that the geology of the Earth was reasonably radically affected by this event. We have yet to sort that out, but that's only an insight that's come in the last few years. Next, please. Now, in fact, our dream really was realized from the return of the lunar samples. Where is the information about the early history of the planets? In fact, a significant part of it lies in the geological record of the moon. We found that the rocks were billions of years old. In fact, if we do the same clock for the moon, it's almost the inverse. It's the very early afternoon hours, not the late evening hours, which are preserved here. So you can see, in fact, that most of the moon, this heavily cratered surface, dates back from the first few percent of the history of the planets, not the last few. So we began to see a host of processes that were operating in that early history that were giving us insight into what the formative years of the Earth look like. Well, let's move up in size a little bit and think of the next largest inner planet body. You can see here on the left that that would be Mercury. In fact, it's 1/3 the diameter of the Earth. It's the innermost of the planets here, closest to the Sun. And interestingly, we find from Mariner 10 data that it has a heavily cratered surface. It looks like the moon on the outside, but on the inside it has a gargantuan iron core. Its density, as you can see here, is almost the same as the Earth's, yet its surface looks like the moon, as best we can tell. Now, we haven't seen all of the body, but why does something look so much like the Earth, have a magnetic field, seem so dynamic on the inside, and yet have a surface that hasn't been modified seemingly for billions of years? We don't know the answer to that. We see some features on the surface, as illustrated in the next slide, that suggest, in fact, the planet, as you can see here, has undergone major changes. What this is a view of a scarp that is a cliff on the surface of Mercury. If you're walking on this way, you would, the sun is coming from this direction, so you're dropping off here. If you got to this point, you would drop down about 2 kilometers. It is a major scarp, unlike any we've seen on other planets, and probably represents the global shrinking of Mercury as a whole as it cooled and condensed. And in fact, many people think that this large-scale change of the surface may be how plate tectonics started on the Earth. We, in fact, don't have a clue as to how plate tectonics started on our own home planet. This provides one model. Changes in the radius of a slight amount could, in fact, cause the underthrusting and subduction that typifies the Earth. In a few years, we'll be launching a messenger mission to Mercury, and it will, before the end of this decade, go into orbit around Mercury and provide global coverage to help us understand this enigma. Is the high density of Mercury due to the fact that it's so close to the Sun and dates from a period of time in which it formed? Or is it, in fact, as many people think, related to the fact that a large impact stripped off the crust and sent it into the Sun? These are two very different scenarios, and they have a lot to say about the early history of the planets. Next, please. Now, as we move up in size, we get to 1/2 the diameter of the Earth. This is a wonderful planet called Mars, extremely exciting, undergoing intense exploration at the present time. This is Mars. You can see it doesn't quite cut the mustard in terms of sizes of Venus and Earth, but it's 1/2 the size, and in fact has an atmosphere, a carbon dioxide atmosphere. The next slides illustrate, in fact, the characteristics of some of Mars. Here it is with its atmosphere. You can see some of the basins, the frost, the volcanoes with clouds streaming from them, and so on. We have an experiment in orbit right now called the Mars Orbiter Laser Altimeter, which is getting precise data. It could tell the difference between the top of this podium and the floor with this laser beam, and in fact is building up a topographic map such as the one you see on the right. Absolutely fantastic information, which is giving us new insight into the topography of the planet. You can see lots of impact craters, ancient crust. You can see big impact basins like the ones we saw on the Moon, further testimony to how important this must have been in the early history of the Earth. Next, please. The landforms are remarkable. We see volcanoes that are, in fact, 25 kilometers high. Now, the next time you're flying at 35,000 feet in an airplane, hopefully in an airplane, just do the math about how much higher you would have to fly to get over this one volcano. It's just unbelievable. So you can see here Olympus Mons, the volcano on Mars. Here's Mount Everest. Here's Mauna Kea above the base of the ocean. This is a large volcano. How do you get these large volcanoes? Here's another one right near it, Arsia Mons. Okay? Look at this gigantic volcano, large caldera structure, flank eruptions, hundreds of millions of cubic kilometers of lava pouring out onto the surface. How do you get that? Large scarps, large canyons. A canyon that is the same distance, an equivalent distance as from Seattle to Miami Beach, stretches across portions of Mars. How do you get such a large structure? Very different than what we see on the Earth at the present time. Next, please. We also see some very remarkable features. On the left here is an impact crater with a low-bait ejecta deposit. A projectile hit this point here, ejected material out, and it looks like you dropped a ball bearing into a mud puddle. And that may exactly be what's going on here. Not so much the ball bearing, but in fact something into very, very fluid or liquid material with water in the subsurface, perhaps liquid water, perhaps ice that got melted. We also see evidence for channels. These are in fact depressions. They look just like river valleys. They're over a significant portion of Mars, and there's strong evidence that water, in fact, poured out on the surface of Mars in its past history. Next, please. You can see here on the left, very, very large channels. These have obviously been shaped by water flowing across the surface. You see these little teardrop-shaped islands here, but look at the scale, 75 kilometers. Vast quantities of water came pouring out on the surface of Mars in its past history. And in fact, many people believe, and we have data from our recent experiment that supports this, that much of this water flowed into the northern lowlands and created a large standing body of water in the northern lowlands of Mars that was there for hundreds and hundreds of millions of years. So Mars is likely to have had oceans in its past history. This certainly changes the equation in terms of the presence, the possible evolution of life, and its possible presence even there today. Next, please. Now, when we take a look at the polar caps on Mars, this is something that is quite remarkable as well. Mars does have water ice and CO2 ice polar caps. They're quite significant. We see evidence for waxing and waning of these caps in the past history of Mars. Sounds a lot like Earth in a lot of ways. Ice ages on Mars, without question. And when we look at the high-resolution data taken of these polar caps, we see layering at all scales. The higher resolution data we get, the more layers we see. What does this tell us? It tells us that there's some cyclic process going on, and we hope to be able, as we've done on the Earth, to crack the code of these cyclic variations and actually get at climate change on Mars, and in fact compare it to the Earth. The holy grail for climate change, in some people's opinion, is comparing these things. The record is preserved out there on Mars, and it's quite remarkable. Next, please. Shown here on the left are similar kinds of layering in the South Polar region. It occurs at both polar regions, and quite remarkably, at another scale, we see stripes on the surface of the planet. This is Mars. These different colored stripes are actually stripes detected by the magnetometer that's in orbit around Mars, and in fact, it appears that there are these linear stripes with different polarity, if you will. The first discovery is that Mars had a strong magnetic field in its early history. Secondly, that it appeared to oscillate back and forth in terms of sign. And thirdly, that, in fact, it magnetized portions of the crust with stripes that are very similar to the kinds of things we see on the Earth's seafloor just off your coast here to the west. Could this mean, and some people have proposed this, that plate tectonics operated as a process early in Mars history? If so, how long? If so, why did it shut off? What does this have to tell us about how the things work on the Earth and how it started? Next, please. We've also roved around on the surface of Mars. The Pathfinder mission was amazing in its sense of exploration and discovery and involving every person on the planet that wanted to tune in by way of the web in this exploration. Absolutely fantastic. We were able to go as a geologist. This was very exciting for me. Viking, as wonderful as it was always a little bit kind of over the hill. We couldn't quite get to the rocks. Here we could go, get up to them, and as you can see, have auto accidents with them in some cases, kick them over, go around to the other side, and so on. This is a geologist's dream, and an immense amount was learned from this, including diversity of rock types on Mars and some very special information about the nature of the surroundings of these landing sites. Next, please. And of course, we've had rocks delivered from Mars to us. The meteorites collected in Antarctica and elsewhere on the Earth that have been demonstrated to come from Mars raise the question about the possibility of life on Mars. You know, several years ago, scientists proposed, in fact, on the basis of several lines of evidence that these materials in these rocks that were blasted off Mars and ultimately landed on the Earth, in fact, were fossil life from Mars. This is very highly debated in the scientific community. Nonetheless, even if it is shown to be wrong, it has completely changed our thinking about the origin of life, the evolution of life, and places where life might exist on other planetary bodies. Witness the astrobiology program here at the university and elsewhere around the world. Next, please. Now, when we sit and step back and think a little bit about what T.S. Eliot said, we can pause for 1 minute here and look at what we've learned so far. Shown here on the left is a series of geological maps. Believe me, I won't bore you with the details, just go for the colors. Yellow, in fact, represents very ancient cratered terrain. This is stuff dating back to the earliest history of the planet. And colors of blue represent, in fact, volcanic activity, resurfacing of the planet by volcanic activity. It's very clear that for the Moon, Mercury, and Mars, we in fact have that record of the first third to half of solar system history. Shown on the right is a plot of the origin of the planets up to the present. Remember that the Earth, here we're looking at the percentage of the surface that's left on the planet as a function of time. The vast majority of the Earth, in fact, dates from the relatively recent period. These are the ocean basins, which are very young. And only a small percentage can we find from back here, and almost nothing from the first half of solar system history. But look at this. The Moon and Mercury and Mars provide that information for the first half of solar system history. And we've learned a lot. We've learned about impact cratering as a process, tectonic activity, how plate tectonics might have started on the Earth, possibly even how continents form, and a variety of other things that are fundamentally important to our perspective on planet Earth. But the goal remains, of course, at this point, what's going on that twin of Earth, the planet Venus. It has approximately the same size, approximately the same mass, approximately the same position in the solar system. What does that planet look like? If all these others show differences and sort of ancient surfaces, what's going on? Is Venus like these bodies, in which case size is not the most controlling factor? Or is Venus like the Earth, and therefore maybe has plate tectonics and has a young recycling surface? This is again, a holy grail, if you will, of trying to understand the relationships among the planets. The next slides, please. Now, in fact, you can see here the sizes and densities and the comparisons of the body, the closeness and the similarities in blue and green between density and size and so on. And this provided an incentive for exploration of the planet Venus on the part of the Soviet Union. They sent over 20 missions to the surface, some of which we were involved in. The next slides illustrate the fact that the problem with Venus is that it's a geologist's nightmare in that you can't learn much from orbit by standard means. Okay, it has a very dense atmosphere, CO2 atmosphere with sulfuric acid clouds. Very difficult to get through. The Soviets, with a master mind of technology, really penetrated through those clouds and landed on the surface. And the U.S. used radar probes to penetrate through the clouds to get images of the surface. Shown here is an old map of the surface of Venus from Pioneer Venus days, in which you could see the yellow areas that looked a bit like continents in a sense that they were high relative to the surrounding terrain, and a lot of low areas in the surrounding area that were in fact lowlands that could have been old ocean basin-like structures, even if there wasn't any water on the surface because of the very high surface temperatures. So the next slides illustrate the fact that the Soviet Union was able to send these probes into the surface and start with the U.S. to get an idea of what was going on the surface. We had to ask a couple of questions. If, in fact, the planet was Earth-like in nature, in terms of its size and density, how did it get rid of its heat? For example, if we take a look here, the Earth gets rid of its heat largely by plate recycling. That is, we keep turning over those lithospheric plates, seafloor spreading, continental drift, etc. gets rid of an immense amount of heat. We know the innermost of the Galilean satellites, Io, is constantly volcanically active. It's getting rid of its heat by advection, which is simply the transfer of heat from the interior to the surface by lavas, and then the radiation of that to the surface. We know that the Moon, Mercury, and Mars have one-plate planets. They're global lithospheric plates. They get rid of their heat simply by conduction. They're just really good radiators. They just get rid of it by conduction. So where does Venus fit in this whole thing? Is it like these smaller terrestrial planetary bodies? Is it like the Earth, or could it in fact be like Io? Well, we got some information from the Soviet missions shown in the next slides. You can see here 7 landings that they did in various parts of Venus. These are several thousand kilometers apart. And here's just one view from Venera 14. They had not only images of the surface, which were really revealing in terms of the details of the geology, but we were able to get actual measurements of the composition from X-ray and gamma-ray data, experiments, and very clever experiments, and learned that these were basalts, much like the seafloor basalts, with some variations on themes that were very important in telling us what was going on there. Then we were able to put this into the context geologically, next slides please, with the Magellan data. Magellan went into orbit around Venus in the early 1990s, and in fact got us global coverage at a couple 100-meter resolution of an Earth-like planet. This is an Earth-like planet without oceans. This is a lot of data. We're talking terabytes here. And in fact, when we take a look at something like this, we can see this is a global view of the surface. Here's a rift zone coming down here, and this image here is from this position here. These cracks here are a few kilometers across, a giant rift zone with fractures. You can see lava flows coming out from this rift zone. In fact, we've learned a lot about terrestrial Earth rifts because, in fact, on the Earth they're eroded away, filled with water, and so on. We can actually look at these examples uneroded and learn a lot about what's going on the Earth. This is just one of the many views that told us about the geology of Venus. We're trying to piece these views together to see if this planet was like the Earth or different than the Earth. Next, please. Now, when we took a look at this, we saw a lot of volcanoes, hundreds of volcanoes on the surface. And in fact, we could look at them from a perspective view with the topography and see them several kilometers high. It looks a lot like volcanoes in Hawaii, etc. And you can see lava flows emanating out from the surface, going hundreds and hundreds of kilometers. They were helped in that by the intense surface heat on Venus, which caused them to cool less rapidly. Next, please. We saw fantastic views of structures we were not familiar with. This is 30 kilometers across. It's a large, viscous dome. It comes out of the surface like toothpaste and piles up around it like a biscuit, if you will, like domes that are in the middle of Mount St. Helens that explode catastrophically. But on Venus, the high atmospheric pressure keeps them from exploding. We sent a copy of this to Arthur C. Clarke, and he wrote back immediately saying it certainly looked organic to him. And in fact, there's another one right next to it, and he was sure that some kind of cell separation was going on. And I'm waiting for the book to come out any minute. We also were able to see impact craters. Look at the details of this impact structure that occurred on the surface of Venus not too many tens of millions of years ago. And in fact, it shows the interaction of the ejecta with the atmosphere and flows and fluid flows that come out from these things. These pictures are amazing, and I encourage you to go to the Magellan website and just feast on the array of features that we see there. Next, please. Now, when we stepped back and we looked at the surface to try to make some sense out of it after being in orbit for a couple of years, we began to see some very interesting things. Shown on the left is a picture of Venus, a perspective view, and you can see volcanoes in the background. You can see lots of lava flows on the surface. Take a look here, for example, at lava flows all over the place. There's one impact crater back here, and that's pretty much it, I think. I don't see any others here. Very lightly cratered surface. That means it's young geologically. It's sort of like the Earth's surface, maybe 300 to 500 million years old. But we could also see that there were some areas here that were very heavily deformed. These look like continental regions. This is about 1,300 kilometers across. And in fact, you can see how heavily deformed the rocks are compared to the smooth plains out here. You can also see the smooth plains are covering this up. So these plains, like here, are younger than this ancient, heavily cratered terrain. But how old is that heavily cratered terrain? Is it like the Earth's continents, a couple billion years old? Is it like the moon's highlands, several, 3 to 4 billion years old? Or what? Well, we thought, why don't we just go count the craters here and compare them to the number of craters here, and that way we'll be able to see where the old areas are and where the young areas are. So we busily got our nose to the photos and mapped every crater out, put them in the computer, and then one day we plotted out the whole thing. And the next slides illustrate what we found out. Shown on the left here is 6 plots. 5 plots are randomly generated points on a sphere projected in this way. Just a simple random generation of points, okay? One of these is the distribution of impact craters on the surface of Venus. And frankly speaking, I can't remember which one it is. What you see here is that it's actually this one, but I'm sure the discerning people in the audience already had that figured out. But the fact is, you cannot distinguish the distribution of impact craters on the surface of Venus from a completely spatially random population. Now, that's saying something. That's really remarkable. It means that those 2 different terrain types, even though they're very heavily deformed in one case and not in the other, you can't distinguish their age on the basis of impact cratering. That means they formed geologically in a relatively short period of time together, and that's saying something. Not only that, when we did count the number of craters up, there are not very many craters. So in fact, when we take a look at them, we find that the age of the surface, as I mentioned, is 300 to 500 million years old. Not only that, when we looked at craters that are on the surface of Venus, the next thing we did was to look for craters that have been bathed by lava. So we could say, oh, well, there's a lava flow covering that crater. That means the lava is younger than the crater. Virtually all the craters on Venus are superposed on top the lavas. What this means is that there was some event in the relatively recent geological history of Venus that completely resurfaced the planet, that wiped out all the craters, that flooded the surface with lavas, and then soon thereafter that stopped and craters started to accumulate. And you ended up with a distribution of craters that look like this. This is like, you know, we thought, will it be A, will it be B, will it be C? It turned out to be D, none of the above, okay? I mean, nobody expected this. And the next slide illustrates what this means. If you take a look at this plot, remember we were wondering whether Venus goes here or here. In fact, it's here. The good news is it's Earth-like in age. That's quite remarkable. The disturbing news is it doesn't have anything to do with what's going on at the Earth at the present time. It's something else. The implication is that internal evolution of Venus in relatively recent geological history on an Earth-like planet overturned sufficiently to completely resurface the planet in a period of geological history that we count on as the period of life, extensive life on the Earth, the Phanerozoic, the last 500 to 600 million years. So on Venus, while life was beginning to get out and really do it right on the land, etc., the surface was overturning on Venus, and a cataclysmic resurfacing of the planet was taking place. Could this happen on the Earth? We don't understand what's going on Venus well enough yet to know. Could this be what the early Earth looked like? There's some promise. Maybe those heavily deformed areas are the continents. Maybe that's how continents get going. Maybe that's how plate tectonics get started, some large overturn like that. But it's still disturbing that it's happened so recently in geological history of Venus on a planet that's so similar to the Earth. Probably what happened is that there was an overturn of material in which some of the material was deformed and pushed together, and other parts of the material came up and was volcanically in place at the present time. There's several scenarios for this. They're all being worked on, but there is no certain answer to how this occurred on Venus. It's still a matter of debate and study. Next, please. Now, if we sit here and think about the terrestrial planets, surely we've learned an immense amount about the evolution of the Earth from these bodies, but there's more to be learned. And in fact, as we look to the outer solar system, we see the gas giants and the satellite systems around them. They're miniature solar systems, which give us tremendous perspective on what's going on our home planet, because we can look at the differences in the satellites as a function of distance from the planet and the forces that are driving their evolution, and get some perspective, comparing them to the solar system as a whole. Now, when we take a look at what's going on here, we see we have to move out here from Mars. You are here, here's Mars, and we have to go through the asteroid belt to get out here for a quick tour. And you can see the asteroid belt contains a whole series of small bodies which are quite remarkable. Those with comets form the fundamental building blocks of planets. And the next slides illustrate a couple of these. You can see here the comets. You had a lecture here only a few years ago which described, in fact, the Shoemakers describing their wonderful discovery of the Shoemaker-Levy comet, and in fact, the breakup of this, its evolution before it in fact collided back into the surface of Jupiter. Quite a remarkable show to have happen in your lifetime. Comets are fundamentally important in organic chemistry and the evolution of the solar system, and they are in fact the building blocks of planets and production probably of the atmospheres. Next, please. Of course, the asteroids are equally interesting and important, and we've been fortunate in the case of the last few years with the Galileo spacecraft to fly by Gaspar and Ida. Here is, in fact, Ida, and you can see here one of the discoveries of our encounter with this body was a small moon, Dactyl, which in fact orbits around Gaspar. I mean, if you can imagine the idea of discovering a moon around around an asteroid, it's just like unbelievable. We almost missed it. But in fact it was found, and it's changed our thinking immensely about how these bodies evolve. And of course, from the Near-Earth Asteroid Rendezvous mission, we've flown by Matilda, and the next slide's just a little over a week ago. In fact, a week ago yesterday, we actually went into orbit around an asteroid. I hope you're all familiar with that and can go to the website to look at these beautiful images. We're now in orbit around Eros, the asteroid, and in fact you can see some of the detailed texture and structure that we're beginning to see and map with a complex of instruments that will really give us an idea of how these things form and evolve. Quite remarkable. In these few years, we can go from thinking about these as points of light to actually going into orbit around one. Next, please. Now, these things also hit the Earth. One of the things we've learned is that there is this body of objects called Earth-crossing asteroids, and it's unfortunately just a matter of time, in fact, before they in fact impact the Earth. You can ask the dinosaurs about that. They kind of learned about it the hard way. So this is something we have to learn about and understand in terms of the evolution of these bodies, not just as building blocks, but actual things that are capable of quite a bit of destruction. We know that in Earth history, evolution, organic evolution, has been punctuated quite often by impacts of these large objects. Next, please. Now, just to finish up here, I want to briefly take a quick tour through the Galilean satellite system as an example of other satellite systems that we see in the outer planets. Again, these are small solar systems. If we take a look at the distribution of these bodies around Jupiter, we find, in fact, that they're arrayed around them in a wonderful way. These are like small planetary bodies. This is the size, Ganymede is the size of Mercury. These are more or less the size of the Earth's moon, and they're each individuals that have their own personality. They're quite different. You can see Io and Europa here doing a tidal dance that causes, next slides please, on Io, volcanic eruptions that have been observed for many, many years. These are some of our very recent observations from the Galileo spacecraft. You can actually map these out. This is a volcanologist's dream to be sitting there and watching these things erupt, looking at the amount of time it takes for them to erupt, looking at the changing styles, and understanding how Io is losing its heat from all these things. Here you're looking straight down the pipe of an active eruption. Just absolutely fantastic. And the next body out, Europa has this outer 100-kilometer deep ocean. Okay, so if you've seen the movie Waterworld, freeze that over and you've got it, okay? In fact, we probably can fly a mission to Europa for what it cost for Waterworld, but that's okay. But imagine this, will you? A 100-kilometer deep ocean, frozen over at the top, overlying a solid silicate body. What's going on there in terms of the evolution of the biota, if there is one? What's going on in terms of whether the water's still liquid today? These are the kind of questions we're asking. The next slides illustrate a surface, if you will. This is, here's a scale here, 10 kilometers. This is a portion of the surface of Europa, and we've removed, the white area is this matrix material we've removed. This high-resolution view goes right in here. You can see these fragments, okay? These are little fragments, actually big fragments of ice. The material around them is melted away, and these things have rotated, tilted, translated up to tens of kilometers in distance. And in fact, it looks like there's been some sort of melt-through, and that these things appear to be things like icebergs floating around. This is debated in some ways, but it's very clear there's been heating, major movement of these features, and the most visible similarity is with icebergs that might be rotating and translating. It must mean that not too far below the surface is, in fact, a liquid water body that, in fact, is causing these things to break up. Heat is there, it's breaking it up, and they're moving around. This is water ice. There's an ocean underneath these things. Is it solid? Is it partly liquid? What's going on? We're able, with the Galileo spacecraft, to keep going back and looking. You can see here, this little area right here, we'll tune in on that in the next slides. On the left, you can see here's one of those areas where this thing is tilted. Here, this is a plate. Here's an iceberg-like structure here. And over here, you can see the same thing, which we plotted here. This is tilted up just like an iceberg. This is the Titanic for scale, you can see. If you look closely, you can see Leo on the bow. You know, it's a... Next, please. So something really interesting is going on there. We see surface discolorations on the surface. This is the same area. Look at this brown material here. The mapping spectrometer on board the spacecraft is showing this has unusual properties and probably represents material from deeper within the ocean that is actually getting its way to the surface. So in fact, we may have communication. This surface is very young, very active. Something very fundamental is going on here in terms of the evolution of this thing. And if in fact there is life here, there's lots of activity geologically that may be bringing it to the surface and maybe showing us lots about what's going on. Now we have Europa Orbiter on the books right now. There are a number of proposals into NASA to do this mission. We hope in the next year the decision will be made to go ahead with this and actually go into orbit around Europa in a few years and make measurements that will tell us what's going on with depth and where we might want to land in the future, perhaps to send a probe through to explore the ocean underneath. Incredibly exciting. Next, please. Finally, we have this zoo of planetary objects in the outer solar system. When we take a look at the surfaces of these satellites we just looked at, the Galilean satellite systems, Io, Europa, Ganymede, and Callisto, you can see as we move out from Jupiter, Saturn, Uranus, and Neptune, that to scale, we can see here the array of objects that exist out there. There are other solar systems out there, miniature solar systems, and many of them have objects like Titan, which are extreme interest from a biological point of view. Titan has an atmosphere. There are probably methane and other like materials on the surface that might form oceans, and the Cassini spacecraft, a Galileo-class spacecraft, is on the way to explore this miniature solar system. So there's many things that are in store for us as we move along to try to understand the characteristics of this whole zoo of objects in the outer solar system. Next, please. Now, of course, there are things beyond the neighborhood. More and more every day you read of new planets discovered around other stars, and it's not going to stop in the near future as instruments get better and capabilities get better. In fact, you can see here the distribution of the terrestrial planetary bodies and just a few planets around other stars. The message here is, in fact, that we're getting to know our neighborhood, but we're just beginning to travel to distant lands in this perspective here. And once again, you know, we're not in Kansas anymore. It doesn't look like the few that we've seen so far are anything like the Earth. 8.1 times the mass of Jupiter, more or less at the orbit of Venus. You know, it changes the dynamics of the solar system a little bit. So it raises the question again, where do we fit in the context of these other bodies? Last slide, please. Now, if we come back to our own home planet Earth, what about T.S. Eliot? So what are the lessons for the Earth? Well, clearly, there's a number of lessons, and they're very important to get our perspective on our own home planet. First of all, we found from all our exploration that the Sun is a star, and it's variable at several timescales. It's changed as a function of time, and there are variations within that that have had profound effect on the planets, their atmospheres, polar wandering, all sorts of things going on, and changes in the atmosphere. In fact, we find that conditions on the Earth may once have been like a snowball Earth in which not just the continents were frozen over, but literally the whole surface was frozen over, and that may have had something significant to do with the radiation of life following the thaw of that period of time. The second point is that planetary orbital parameters are variable. We see lots of evidence for changes in obliquity of the orbit of the planet, changes in the eccentricity of the orbit. The planets influence each other, and we can see these things mapped out in evolution of the Earth, of Venus, and most of the other major planets. Very, very significant things that we see that are changing our perspective about what drives variations in geological activity on our Earth. And in fact, it's clear that the Earth-Moon distances change with time, and this has had profound effects on the intertidal zone, which is really the cradle of much of the latter-day evolution of life. A third point is that impact cratering is a common process, not like I thought when I got my geology textbooks as a freshman, but rather it's a very common process. The big one may have caused, in fact, the Moon, and of course this would radically influence the Earth. Life may have arrived on Earth as ejecta from Mars. Think about that for a while. Impact events clearly have punctuated biological evolution, and an impact event may have paved the way for humans, and in fact, an impact event eventually may terminate humans. These things can be quite big, as I illustrated in some of the slides. A fourth point is that the generation and loss of heat from the inside of the planet can have very radical effects on the surface geology, and they can't be just pushed back to the early history of the planets. Venus tells us that radical changes can occur. Big plumes on Mars, large-scale overturn on Venus, some very important things, not only to think about for the future, but also to learn from in terms of the origin of continents on the Earth and lots of things that went on in early Earth history. Fifthly, the ingredients that probably led to life are common in our solar system. Organic molecules, heat, water. When we look at the Earth, Mars, Europa, Ganymede, Callisto, Titan, comets, meteorites, scores of outer planet satellites, they all have these ingredients. We live in a situation in which we have lots of laboratories to study the conditions that have led to life. We hope we know what we're looking for, but as for me, I'm convinced that, in fact, given those ingredients, that the situation on Earth is probably not unique, and in our lifetimes, I think we'll be getting big news about life in other parts of the solar system and possibly in other parts of the cosmos. And finally, let me say that, in fact, our solar system, as we look at it and start to compare it to others, seems a little bit unusual compared to others, but we need more data, okay? Yes, we're beginning to know the place for the first time, but also remember that almost everything is not yet known. Thank you very much.